Okay. So, you're going to see something very familiar known as the equilibrium expression, or another way that they describe it is law of mass action. Okay? The expression obtained by, that's a long wordy definition, obtained by multiplying the product concentration and dividing by the multiplied reactant concentrations for each and each concentration is raised to a power represented by its coefficient. Okay, so there's a thing called an equilibrium constant. I'm going to kind of really just explain both the equilibrium constant and the equilibrium expression on the next slide when we do it. Okay? So write the equilibrium expression for this. This will look familiar. You will not find this overly difficult. So this K is your equilibrium constant. You have a spot to write this in, right? Yeah. Okay? And the equilibrium expression is when you plug in the concentration of your products over the concentration of your reactants raised to the power of their exponents. Yay, it's snowing. It would be awesome if we got out early today. We can go home and sleep. I shouldn't say that on camera.
That'd be awesome.
I would love to sleep right now. I should sleep.
I actually want to sleep.
Or just like read a book or listen to music, looking at snow, fireplace going.
Why did you read a book?
So romantic. You're such a romantic dude.
No, it's relaxing. Just fire.
Did you get your jacuzzi with candlelit?
I don't want to paint.
I mean, if someone bothered me.
Right, if like we got a free one, yeah.
That was really a stab at you. Alright, anyways. I played basketball yesterday for the first time in a while. Don't get old. Don't do it.
That's playing basketball.
Oh, I am so sore. Also, when you don't play basketball very much, you try to play basketball again, you end up just hurting your own pride. That's why you play children. That's why you play against high schoolers, I guess. No, I'm kidding. It's not the same here. We got some good high schoolers here. Like Grant. Okay.
Speaking of, good job. That's the night I actually watched that game.
What?
You win. Yeah, the first game I booked.
Oh, I had to work.
Oh, I saw you there. I was like, wow. Grant's here.
And her dad was reading a book during.
Yeah, it was like Marriage Matters or something like that.
Yeah, it was some like pamphlet.
I want to go up to him and say, "Are you having a marital problem, sister?" Alright, so this is how this works. I need to probably go a little quicker here. Your equilibrium expression is going to be your concentration. Again, your brackets represents concentration. So we got NO2. We're going to raise that to the power of its coefficient. You guys remember this?
Yeah.
Multiplied by the other product concentration raised to its coefficient power. It's always products minus divided by reactant concentration. NH3. The fourth power, O2. Ah! You right. Like that. So, if you don't remember this time of year, man,
So your room is safe.
it pretty much is. It makes me feel overwhelmed.
Well, it's a Willy Wonka got out of the candy business into junk business.
I know, right? Okay, so this whole thing is called the what? Yes. Okay, your K is your equilibrium constant. The whole thing is what we would call our equilibrium expression. So we can figure out the equilibrium constant K at a specific temperature by knowing, or if we know the equilibrium concentrations during a given reaction. Okay. From that, everybody get this? Can I erase it? We can figure out what the K is, or the equilibrium constant is, for a given reaction if we know the equilibrium concentrations. So, you are actually going to find the K for 3 different things. It's going to be a little bit of work, not going to be overly difficult. Okay? What these are your equilibrium concentrations. Then I want you to find or calculate K if this is your reaction. Calculate K if you reverse it, and calculate K if you multiply the reaction by a certain factor. So, do I need to show you one, or what do you think you have to do here?
Just write it.
Yeah, and then you're going to do what after you write the expression?
Plug in concentration.
Plug in concentration, solve for K. Everybody understand that? You're going to write the equilibrium expression for all 3. You're going to plug in the equilibrium concentrations. Now it's important, it has to be the equilibrium concentrations, otherwise you're solving for something else known as Q, or the reaction quotient. But we'll get to that later. So solve this guy, and then I'm going to show you a unique relationship between these 3 guys, just to save you some time in the future. Temperature? Yeah, that only matters because we're going to talk later about how your equilibrium constant can change if you change the temperature, but if it's at the same temperature, it's always going to be that equilibrium constant. Because later we will talk about the things that can shift equilibrium, and that's what's really important when it comes to practical applications, because that's what people do or big corporations and production plants do all the time. The whole idea is, how can we produce more product? And the best way to do that is to know how to shift the equilibrium as far right as possible.
Moving product.
That's one of the ways, yep.
Remember that
Is
one.
the temperature right?
It will matter in the future. It's just, at this point, it just is trying to show you that all these are at the same temperature, so they're all going to be a constant K. There's going to be multiple different Ks. Got them all down, or are you waiting for everybody? You just did the first one?
I get it right
What'd you get, Emily, for the first one?
then. 3.795, that's the fourth.
Yeah, 3.8 times 10 to the 4th. Now, K is a unitless constant. Might want to write that down somewhere. You're never going to have units for K. Did everybody hear that? You're going to probably need double parentheses. That would be my guess. Unless you divide it by the first and then divide it again by the second. second constant?
Yeah, 2.64 times 10 to the negative fifth.
And here, you got the third. No one yet? Anybody?
I'm close.
Working on it?
I have it. It's like 190 or something. 194.8.
The ones that they were saying figs, I mean.
I probably should have done
The
the
other
other one.
ones that say figs too, but.
So this one you got 190.
Yeah.
Oh, I got 190.
Well, it's sig, they just said
Oh,
sig
okay.
figs.
25.
Technically, it should be these. Okay. Now, there's a relationship between all of these. Okay, these are the same type of equation, right? It's the ammonia equation. What was the relationship between the equilibrium expression of the Ford and the equilibrium expression of this guy? It's the inverse. That's something that's very important. So let me show you a little trick. We're going to say K prime is the reverse reaction. Okay, so K is just going to be representing the forward reaction. That's what it was. K prime is the reverse reaction. And so what you will find is that K prime is the inverse of your forward. So, if I take 1 divided by my forward reaction K, you're going to get your reverse reaction K.
Yeah.
2.6 times 10 to the negative fifth. Now, what is the importance of this? Well, just to kind of save you some time and to realize, okay, if these equilibrium expressions and equilibrium constants are based on the reactant concentrations, equilibrium concentrations raised to their exponents, if you just flip it, you're essentially just taking the inverse. Okay? So what do you think the relationship between the last reaction, we'll say it's prime.
It's the answer for the third one is the square root of the first one.
It happens to be that, I don't know if it's. okay.
Yeah, okay, yep.
It happens to be that. I don't know if it's.
But I'm going to say it a little bit differently because that's true if you take everything by a half. But the principle I want to show you here is anytime you multiply it, because it could be to the 1/3, it could be to the 1/4, then it'd be the cubed root or the.
Oh, so whatever you divide it by is the root, the numerical root of the.
Well, whatever. Well, yeah, if you want to say divided by, yeah, sure. A better way to do it would be your K double prime, which is what I'm representing a multiplied reaction by, is going to be K to whatever you multiplied it by's power. So in this case, we multiplied it by a half. Right? The difference between these two reactions is what?
The coefficient.
Divide by 2, okay? So, anytime you multiply a factor by something, I could have doubled everything. Then it would be K to the second power. I could have tripled everything, quadrupled everything, it would be K to that power. I could have divided everything by 4, it would be K to the 1/4. Does that make sense? I just a quick way to be able to figure this out. So 3 0.8 times 10 to the 4th to the 1/2 power should give you about 190. So you know, if you get the K of the forward and you can figure out what the relationship is between your forward reaction and what your reverse or whatever you're multiplying by, save you a few minutes. Okay? And I think that's what this is summarizing. Everybody get that? Right here's just kind of some conclusions. It's just saying that your forward and your reverse are just the inverse of each other, and the relationship between if you multiply by a factor. Oh, and there's where it says your K values do not have units. I didn't know that was in there, so sorry for making you write it in. Okay, end on this. We are going to do one more problem, but I do want to kind of spend a little bit of time talking about this. We are going to open up our book for a sec. Turn to page 600. Look at the table in the bottom there. Experiment 1, experiment 2, experiment 3. Just take a look at that. And I want you just analyze that table for a second. I'm going to ask you a question. What do you notice about this table? Is there any inferences you guys can make about what this is really trying to show you? ACT 101 right here.
The change is a lot less from
Okay.
at least for the SO2.
Wait. Page 600.
Oh, I'm sorry.
Bottom. Okay.
On there, I just wasn't looking
Can't make any inferences.
Yeah.
What was that?
K is the same for all.
Yeah, K is the same for all of them, but your equilibrium concentrations are what? Different.
Initially.
Okay, so there's a big inference you can make here then. At a given temperature, what's true?
Equilibrium constant is the same.
The equilibrium constant at a given temperature will always be the same regardless of how much concentrations of each thing you have at the beginning. Okay? So in theory then, we will always have one equilibrium constant at a specific temperature, but there is really an infinite number of equilibrium positions. What do I mean when I say equilibrium positions?
The ending concentrations are.
Equilibrium concentrations. So you will always have the same constant, which is really the ratio. So essentially this is like the stoichiometry idea with the whole recipe of the balanced chemical equation, right? If you've got if a particular reaction always has the same ratio, you're always going to maintain that for your K. Your K will always be constant, but you could scale up or scale down your equilibrium concentrations, but the ratio will always stay the same.
You said at one temperature, so if the temperature changes.
Yeah, K will be different at different temperatures, but that's only because you're shifting.
How quickly does it change? If you add 3 degrees Celsius.
Probably pretty quickly.
Okay.
Yeah. I mean, it depends on the rate, but usually.
So it wouldn't be
close necessarily, just 50 degrees, it wouldn't be very close to each other.
The K's aren't going to be that much different from changing the temperature.
Okay.
It depends. It's going to depend on the reaction. Okay?
I'm thinking of the multiple choice question in the test already.
Really?
I'm thinking of multiple choice questions, you're gonna be super close to each other or not.
We'll talk about
Okay.
some more stuff as we get
Okay.
through here. All right? Really important. Okay, it's really important to know not only what equilibrium is that the rate of the forward and the rate of the reverse are going to be equal, and that at a specific temperature and with a specific amount of initial concentration, you're always going to get a constant equilibrium concentration. Okay, but not all those equilibrium concentrations will be the same if you change the initial conditions. So, just so you guys can see this, I want you guys to do this and then we'll be done. It says show that the equilibrium constant is the same in both cases. You've got experiment 1, you've got experiment 2. They're the exact same experiment or exact same reaction. Now, technically, you guys will need to write the equation out here before you do this. Is that so long ago that we can't remember how to do that? You guys write the equation without my help? I sure hope so. Close your books, everybody. Close your books. Close your books. Close your books.
Oh, the sulfur dioxide.
Yeah. Because you're not going to be able to write the correct equilibrium expression if you don't have the correct balanced chemical equation.
Oh, we need to know.
Why do you think you need to balance it? Coefficients matter in any way? Before they even started.
And that just lowers down on.
Drops down on it, just move away from
I think the steam from the soda.
Yeah, they're gonna ruin that drill. They told them they probably shouldn't do that, but
You're right.
yeah.
I mean,
The dad was like, gives me an excuse to buy a new drill. It's like, okay.
And you can make a hole in like a plastic and just put fit the hole to protect it.
A little bit.
Not a lot, but a little bit.
Got an answer?
I don't know. No, that's not
We
right.
just have to do the equation.
Show that the equilibrium constants are the
Oh,
same.
wait.
So you're gonna have to do find the equilibrium constant for both experiment 1 and experiment 2. You gotta know what the equilibrium constant is?
Yeah, I did. But
Can't balance it?
So SO2 plus 2O2
Well, you have to do,
plus SO3.
well, it has to be the least common factor. So it's just 4 SO3 and balance in there.
Do what?
That's 12 oxygen, so.
in order to balance the O3 in the O2.
What did you say?
You're not balanced.
4 SO2 plus 2 O2 goes to produce 4 SO3. And that's 12 and 12.
You forgot how to balance, oh boy.
Can you do 2,
Oh, I
1,
just don't know
and
what's
2?
at the O2 reading.
You're right, the equation's right, you just don't have it balanced, right?
Wait, can you do 2 SO2 plus 1 O2 goes to produce 2 SO3?
You do that.
You can't.
So it's 2 SO2 instead of 2.
2, 1, 2 electrons. Oh, no, I got it.
Maybe I need to have you guys do this more often so you guys don't forget. Your expression will be the same for both equations. You're just going to have different equilibrium numbers. And hopefully, you will get a constant that's pretty constant. Yeah, it's not going to be exactly due to experimental error, but
Just rounding, probably.
and rounding.
Yeah, 0.04 off.
Ooh.
And rounding 1 off.
There's your equilibrium expression. You're going to plug in for experiment 1, experiment 2. And yes, it's going to appear that it's a little bit off, but that's due to rounding, and we don't know if this is, 100% perfect experimental data. What did you get, Rylan?
That's 4.35 first, sorry, 4.36. Second one's 4.315.
So there's really like a 0.04 difference.
Yeah.
Everybody get that? What? Oh boy.
Would it work if you started the initial concentrations or what?
Do the
That's
equilibrium.
the whole point, the I equilibrium is the same.
We don't do
The initial would not be helpful to you.
Oh,
Why
yeah,
do they-
you're going to use equilibrium.
Throw you off, it's a right
It's
here.
called equilibrium expression. What?
So we don't need initial at all, it's useless.
No,
It's
the initial is just telling you that's why you got different equilibrium
Okay.
concentration, because you didn't have the same starting point.
Got it. It's red herring.
What did you say the answer was?